Good afternoon. Today we are going to see Introduction to Fuzzy Logic. The outline of today's lecture will be as follows. First, we have the Introduction to Fuzzy Logic, and then we are going to see about fuzzy sets which form the basis of fuzzy logic. Then we will be seeing the building blocks of fuzzy logic, which is membership functions, and then we are going to see crisp relations. So that in the forthcoming classes we will be having studies about fuzzy relations and inference from fuzzy relations, so that we can form fuzzy rules, which are the building blocks of fuzzy logic control. Let us see the introduction part of fuzzy logic. So, the term fuzzy means hazy, which means unclear, and fuzziness happens if the data or the information is not clearly defined. Is not clearly defined. So, the opposite to fuzzy is, you can say, crisp, and fuzzy logic is designed from the concept of fuzzy set theory, which is nothing but extension of classical set theory. In the fuzzy set theory, we have the degree of membership. In fuzzy set theory, we have something called degree of membership, or something called membership grade. Sometimes it is called membership function value. For each element that is present in a fuzzy set. So, the value of a membership grade will be lying in the interval of 0 to 1. So, accordingly, a membership function is related to a fuzzy set, say for example A, in such a way that each element x of A is assigned to a membership value of 0 to 1 interval. So, it is characterized, the membership function is characterized by an expression, I can say the membership function grade or membership function value is characterized by an expression, this, which indicates that x belongs to fuzzy set A, x is a member of fuzzy set A, and the membership value of x is given by mu A of x, such that it takes the value 0 to 1, where x belongs to the universal set x. So, when I say x is the universal set, what is A? A is nothing but a subset of x, where x basically represents an object or an attribute. Thus, fuzzy set can be expressed or defined as, a set of ordered pairs can be defined as a set of ordered pairs which is given by A equal to a set of x comma mu A of x such that x belongs to the universal set X, capital X. So, X here is universal set or universe of discourse, and mu A of X is nothing but the grade of membership, of object X present in fuzzy set A, such that mu A of X will lie in the interval between 0 to 1. Okay. Now, let me also express or give the definition of fuzzy subset. Fuzzy subset, let us say fuzzy subset F. A fuzzy subset F of a fuzzy set A can be defined as a set of ordered pairs F equal to x comma mu F of x such that x belongs to set A, where the first element is an element of the set A and the second element is a value in the interval 0 to 1. Now, let us see an example to understand more about the fuzzy set. Now, consider an universal set. Let us consider an universal set, say H, representing the heights of, say, humanoid robots. Okay. Let short, medium and large, or let us say not large, it is tall. Okay, so let us take short, medium and tall be the subsets of the universal set H. Okay, so in that case these subsets can be defined by the user or the designer in the classical approach as, note down, it is in the classical approach. These subsets short, medium and tall can be defined as, say, short equal to a set where height belongs to the universal set such that 1 feet less than equal to height less than equal to 3 feet. Okay, that is defining short, which is a subset. And medium subset is defined as height belonging to the set H such that 3 feet less than equal to height less than equal to 5 feet. Likewise, tall equal to height belonging to H such that 5 feet less than equal to height less than equal to 7 feet. So, here it must be noted that 2.9 feet, here it can be noted that you can see the range for short it is 1 feet to 3 feet, for medium height it is 3 feet to 5 feet, for taller height it is 5 feet to 7 feet. In that situation, when we can say, we can observe that 2.9 feet belongs to short subset, whereas 3.1 feet is belonging to medium subset, which implies that the boundaries of classical set are rigid, they are strict. Okay. That is what our observation is. Okay. In contrast, what we are going to see is, in contrast, the fuzzy set boundaries, the boundaries pertaining to the fuzzy sets are soft, they are not so strict, they are not so rigid. Okay, so one approach to define the fuzzy subsets for the universal set H is shown below. That means, so one approach here is shown below through the schematic of fuzzy membership. Height is basically the member which has the elements which are nothing but short, medium and tall. So, height is a fuzzy variable here which are going to be short, medium and tall. So, the height is defined here in this case feet, whereas this is the membership function of universal set H. Okay. So, x axis is fuzzy, x axis fuzzy variable, the variable, not fuzzy variable, it is a variable height, and y axis is a membership function. So, we can see basically it is a fuzzy variable only, height. So, we can see that this schematic we can see here. Okay, so this is value 1, this is 0.5 membership function values, and the first triangular membership function is short, and the second membership function is medium, and the third one triangular membership function is tall. So, we can observe here one thing, say the height of 3 feet is a member of, it is observed here from this membership function schematic of the fuzzy variable feet, which involves short, medium and tall subsets. We can say that the height of 3 feet is a member of both the fuzzy sets, which are nothing but short and medium. You can say that short and medium involves the value of 3 feet. Okay. So, that corresponds to the 3 feet one corresponds to the membership function value which is mu h of medium is equal to mu h of short is equal to, from the schematic what is the value you are saying, it is 5, sorry it is 0.5 is the membership function value. You must note one thing, that the membership value is going to have in the interval 0 to 1, maximum value is 1, which means that the significance of that value, the relation of that element in that particular subset or set of fuzzy is prominent, it is more. If it is 0, then it is not a member at all of that set. Okay. So, we will continue this topic now. So, let x1 comma x2 up to xn be the elements of set X. Then the fuzzy set A, which is a strict subset of universal set X, can be represented by one of the following or the standard forms, which is A equal to mu A of x 1 upon x 1 comma mu A of x 2 upon x 2 mu A of x 3 upon x 3 up to mu A of x n upon x n, where it is to be noted that mu A of x 1 upon x 1 is not a divisor, it is not something having division operation, rather it is a tuple. Okay, it is a tuple, it is not a division. So, when I say one of the standard forms means it has couple of other standard forms also, which means x 1 upon mu A of x 1, x 1 x 2 upon mu A of x 2 is another way of representing. Another way of representing is A equal to, set A equal to x 1 comma mu A of x 1 comma x 2 comma mu A of x 2. In this way also we can have the representation of fuzzy set A. Okay. So, now we will see something interesting, that is called fuzzy set operations. What are the operations that can be performed in this fuzzy set? This is much similar to the classical sets, which means union, intersection and complement. So, called fuzzy union, fuzzy intersection and fuzzy complement. So, we are going to see here fuzzy set operations. Fuzzy set operations, what are they? So, the fuzzy set operations, as I told, they are three. One is fuzzy complement, the next one is fuzzy intersection, and the third one is fuzzy union. Let us talk about, first of all, fuzzy complement. So, the membership function that is the fuzzy complement membership function mu A bar of x of the complement of A, that is denoted by A bar. Okay. So, mu A bar of x is nothing but the complement membership function. Okay. So, that is defined by mu A bar of x equal to 1 minus mu A of x for all X belongs to the universal set capital X. The pictorial representation of this fuzzy complement is given by the schematic. Okay, so x axis is the variable fuzzy variable x and y axis is the membership function value. So, we have the membership function value coming out to be like this, and we can have something like this, where I can say that okay. So, when I have this being mu a of x, then I have the complement which is given by this, that is called mu a bar of x, which is nothing but 1 minus mu a of x. So, this is the pictorial representation of the fuzzy complement. Next, we have the fuzzy intersection. Next, we have the fuzzy intersection. Fuzzy intersection operation. The intersection of two fuzzy sets A and fuzzy set B is defined by A intersect B equal to x such that x belongs to A and x belongs to again B, which implies that it is an intersection, it is a common portion of that. And we can also say that there are, we can say further about this fuzzy intersection, that there are two significant operators, two significant fuzzy intersection operators, which are minimum operator. Now, another one is a product operator. Let us see first about minimum operator. Mu a intersect b of x equal to mu a of x and mu b of x. So, the AND operator indicates the minimum of the membership function values in fuzzy. So, minimum of mu a of x comma mu b of x for all x belongs to capital X. Likewise, let us see the second important operator under fuzzy intersection, which is product operator, that is given by mu a intersect b of x equal to mu a of x multiplied by mu b of x for all x belongs to capital X. The schematic representation is given by (1.0), this is 1. So, So, this is 1 and another membership function is this. Okay. So, the output of this intersection operator is this is the one, that means this one. Okay. So, that is given by mu A intersect B of x. Okay. So, one here is mu A of x, another one is mu B of x. Okay. So, accordingly we get this as the output, which is again membership function that corresponds to one value, and this is the variable, fuzzy variable. Okay. So, what we have observed here is this is the output of the intersection, that is what I have drawn separately here. Okay. Now, we will see about the fuzzy union one, which is the last of operation, fuzzy operation. Okay. Now, let us see that fuzzy union. So, the union of two fuzzy subsets A and B, or fuzzy sets A and B, is defined by A union B equal to x such that x belongs to A or x belongs to B for all x belonging to universal set x. So, this is an OR operator. So, we are going to deal something called maximum. For the AND operator in the previous case, we were seeing about minimum operator. So, here we are going to deal with maximization. So, maximum using the maximum of that, finding the maximum among the membership function values. So, two significant operators are there under fuzzy union. The first one is maximum operator, which is given by mu A union B of x equal to mu A of x or operation of mu B of x, which is nothing but maximum of mu A of x comma mu B of x for all x belonging to capital X. Another important operator under fuzzy union is sum operator. Sum operator, which is given by mu A union B of x equal to mu A of x plus mu B of x minus mu A of x into mu B of x for all x belonging to universal set x. Okay. So, now this schematic representation is given by, for the fuzzy union is given by x, this is membership. Okay. So, let us consider 1.0 the maximum value, and let us have two functions like this. Okay. So, one function is say represented by this symbol. Okay. So, one function is this, another function is this. So, one function is mu A of x, another one is mu B of x. So, mu A union B of x is given by that is all. That is membership that is a 1.0 here, and this is your fuzzy variable. So, as per this we are going to this one, it is reaching the Okay. So, that is what. So, this is union A union B. Okay. So, this is the resultant of that. Now, let us move on to another important topic coming under fuzzy logic, which is nothing but fuzzy membership functions. Okay. So, typical fuzzy membership functions we are going to see here, fuzzy membership functions. Let us see the first one as the L function, that is defined by L of variable x with the parameters alpha and beta is equal to 1 when x is less than alpha. You will understand this expressions which we are going to get the values of L function by a schematic representation quickly. So, the schematic representation is given here, x, this is your membership, say it is 1.0. Okay. That is all. This is the representation of this L function such that this is your alpha, this is beta, this is beta. Okay. So, when I have alpha and beta in the L function, I can define the value of the L function by L of x is the input parameter with the function parameters alpha and beta becomes equal to 1 if alpha or x is less than alpha. X is less than alpha, when x value is less than alpha, it is 1, and it is going to be alpha, this range I am saying, yeah, alpha minus x upon beta minus alpha when alpha less than equal to x, less than equal to beta, and it is 0 when x is greater than beta. This is it. Now, let us talk about another function which is very important function called S function. S function, that is given by S of x with the parameters alpha, beta, gamma equal to 0 when x less than equal to alpha. Let us see the schematic here. The membership function. Okay. So, here it is gamma, the middle one is beta, the starting one is alpha. So, this maximum value corresponds to 1.0 membership grade. Okay. So, this is the S function such that S function gets the value 0 for x value less than alpha, less than equal to alpha, and it is equal to 2 times of x minus alpha upon gamma minus alpha whole square for alpha less than x less than equal to beta, and it is equal to 1 minus 2 times x minus gamma divided by gamma minus alpha whole square, where x is in the range of beta and gamma, and is equal to 1 if x greater than gamma in this case. Alright. So, this is the S function. Likewise, we have the gamma function, that is given by the next function is gamma function, the gamma function, that is gamma of x with the parameters alpha comma beta is equal to 0 when x less than equal to alpha. Before that, we will see the function takes this profile. This is membership 1.0. Okay. So, this is beta, so this is alpha. Okay. So, in this case we can say that it takes the function takes 0 value for x less than alpha, and the function takes the value which is x minus alpha upon beta minus alpha for alpha less than x less than equal to beta, this case, and it takes the value 1 for x greater than beta. And two more importantly and commonly used functions are triangular and Gaussian functions we are going to see now. So, triangular functions, triangular function, let us see triangular membership function, which is given by gamma of x such that with the parameters gamma of x variable with the parameters alpha, beta and gamma equal to 0 for x less than alpha, where the profile is membership. This is alpha, the middle one is beta and the last one is gamma. So, this is a triangular membership function. So, this takes a value 0 for x less than alpha, less than equal to alpha. So, for x in the range from this to this, it is given by x minus alpha upon beta minus alpha for alpha less than x less than equal to beta, and for this range the function value is gamma minus x upon gamma minus beta for the range beta less than x less than equal to gamma, this range. And in the another range where x is greater than gamma, it is 0, that is all. The triangular function membership function is finished now. Then we have Gaussian membership function. Okay. So, Gaussian membership function, that is given by g of x comma m comma sigma. G of x, it is x is the variable, m and sigma are the functional parameters, which is given by the expression e power minus of x minus m whole square divided by root of 2 sigma, where the parameters sigma and m control the width and center of this Gaussian membership function, which is given by the schematic. Okay, so this is it. Now, let us talk about the crisp relation. Let us talk about the crisp relation, which is the final topic of our today's lecture. Let us talk about that crisp relation. So, like that we are going to see tomorrow fuzzy relation, fuzzy rules, fuzzy inference and fuzzy compositions. Okay. So, coming to the crisp relation, let the Cartesian product of two universal sets is determined as x cross y equal to x comma y such that x belongs to capital X comma y belongs to capital Y. The crisp relation mu r of x comma y is defined as mu r of x comma y equal to 1 when x comma y belongs to x cross y, belongs to the universal set, the Cartesian product universal set x cross y. 0 when x comma y does not belong to x cross y, where the value 1 indicates a complete relation and value 0 indicates no relation at all. So, when the sets are finite, it must be noted that when the sets are finite, the relation is represented by a relation matrix R, capital R. Okay, now let us see an example to understand this crisp relation. So, take an example where we consider two sets x and y. Okay, we consider two sets x and y such that x equal to 1, 2, 3, a set containing the elements 1, 2, 3, and y is a set containing a, b and c. Now, for the above sets, two relation matrices R1 being a relation matrix and R2 being another relation matrix. Two relation matrices R1 and R2 can be defined as R1 equal to x and y. So, 1, 2, 3, first x related to y set. So, the first one represents the row of the relation matrix, the second one represents the column of the relation matrix. Let us see that all the elements of this matrix being 1, 1, 1, and let us have another relation matrix, let us say 1, 2, 3, a, b, c between these two universal sets. Let them be like this, which is 0, 1, 1 and 1, 0, 1, 0, 0, 0, let us say like that. Okay, so here which states that, so it states that R1, in R1 the relation matrix R1 implies that each element in X is completely related to each element in the universal set Y. Each element in set X is completely related to each element in universal set Y, whereas the relation matrix R2 indicates that only the pairs 1 comma b, 2 comma a, 2 comma c and 1 comma c are related, other elements are not related. Now, let us see composition. Under crisp relation, we are going to see something called composition. What is that composition? Let us see that now. Composition. Let us consider three sets, say X, capital Y and capital Z. First, let R be a relation matrix that relating elements from set X to set Y. Similarly, let S be a relation matrix that relates elements from set Y to set Z. Now, let us have the relation which is, let T be the relation that relates the same elements in X that R contains to the same elements in Z that S contains. Again I repeat, T is a matrix or relation matrix that relates the same elements in X that R matrix has to the same elements in Z set that the matrix S contains. So, given R and S, T is determined by principle of composition. By the principle of composition, we can obtain the final relation matrices for a given relation matrices R1 and R2. So, the composition can be min max composition and max product composition. It must be noted that for the crisp relation, both compositions, min max composition and max product composition results in same value. We are going to see that quickly. So, if it is min max composition, then if it is min max composition, then mu T of x comma z is given by maximum for y belonging to y belonging to capital Y of minimum of mu r of x comma y comma mu s of x comma y comma z. Likewise, if it is max product composition, then mu t of x comma z is given by maximum for y belonging to capital Y mu r of x comma y product mu s of y comma z. Okay. So, now in the end we are going to see now a numerical problem to be solved. Let us take this example. Given the relation matrix R, say so given the relation matrix R x1, x2, x3 and y1, y2, y3, y4, that means it relates the elements of two universal sets x and y. Where the matrix elements are 1, 0, 1, 0, 0, 0, 0, 1 and 0, 0, 0, 0. Likewise, we have another relation matrix which is that is between y and z. Z set has two elements z1, z2, x has 3 elements x1, x2, x3 and y has 4 elements y1, y2, y3, y4. Relating R relates x and y, that is why x is in the row, and S relates y and z, that is why y is in the row now. Now, to find T, which is a composition of R composition S. So, T is found out to be in this way. T is R and S. So, we can say that is x1, x2, x3 and z1, z2. It relates x and z. So, we can go by max min composition. So, that max min composition if you take, you will have the first one coming out to be 0 here and 1 here, 0 0 0 1. Due to time brevity, I am just giving the final value and I ask you to solve this problem in the two methods, min max and max product, and any one you can take, say min max. So, if you say by that, you will be having this one that is coming out to be max min, sorry, not min max, it is by max min you can go. So, you can be getting maximum over y belonging to capital Y for the first element I am saying, minimum of mu r of x comma y and mu s of x y comma z. Okay. So, in this way you need to do. So, that gives for the, okay. So, we will be testing it for, okay. So, let me fill this element of 0 1 0 0 0 1 0 0. So, in this case R and S completely we have, that is the input. We need to find the relation matrix that is given by the composition of R and S. So, T is going to be the composition of R and S that will be involving either max min composition or max product composition. So, let us say max min composition of the first element. So, we go this and we go this. So, 1 0 minimum of that and 0 0 minimum of that, 1 0 minimum, 0 0 minimum. So, it is maximum of 0 0 0 0 like that. So, what is the first element? Maximum of 0 is 0, that is why. Similarly, we can go this one and go to this. Okay. So, 1 1 minimum of that, 0 0 and 1 1 0 0 minimum find out. So, the minimum of these corresponding elements of first row of R and the second column of S, that gives max of 4 elements. So, maximum of the 4 elements is going to be 1 here. So, like that you can take second row and first column of S to fill this element. Likewise, second row of R and second column of S to get the second, that is second row second column element of T matrix. Likewise, for the third row of T matrix, go by third row of R with first row or first column of S, that gives this element, that is 3 comma 1, and for 3 comma 2 of your T matrix, go by third row of R and second row second column of S. So, that you will be getting 1. And one thing it is to be noted that using max min composition or max product composition, you will get the same result. That is only the situation for crisp relations. Okay. So, by this I conclude here our lecture today. Today we have seen fuzzy logic introduction to fuzzy logics, then we have seen fuzzy sets, and then we have seen fuzzy set operations or fuzzy operations, which is nothing but the complement, union and intersection. Okay. Fuzzy operations, and then we have seen the membership functions, and finally, we have seen the crisp relations that involves both composition, and we have seen the compositions based min max and max min and max product relations. And for through an example, we found that max min as well as max product compositions give the same result for two relation matrices. With this, I stop my lecture today. We will see tomorrow fuzzy relations with fuzzy rule base. Thank you so much for your patience.